Hello everyone, and welcome to my talk on estimation rates for sparse linear cyclic causal models, which is joint work with Philippe Rigollet. Here we consider the following linear structural equation model. We observe p random variables, x1 through xp, where each value xj depends linearly on the value of all the other random variables, plus an error term epsilon j. We collect this up into matrix form and solve for x. We obtain that x is I minus b inverse times epsilon. We assume that this inverse exists. If on top of this, we assume that epsilon follows a standard normal random variable, then x is Gaussian as well with concentration matrix or inverse covariance matrix that is quadratic in B. Here, the sparsity pattern of B encodes the causal graph G, or the causal relationship between the random variables. And contrary to other places in the literature where acyclicity is assumed, this model can accommodate cycles or feedback loops, which are common in biological systems. Note that with everything I've given you so far, B is not identifiable yet. There are many assumptions one can find in the literature to make it so, but we don't make any of those standard assumptions here. Instead, we assume that we have access to interventional or experimental data. In each experiment, the set of random variables is split up into the sets JE and UE, where the random variables in the set JE are being intervened on, which means that they are cut off from their parents and their values are being set to independent standard normal random variables. Formally, what this means is that we have the same kind of observations, but now part of the B matrix is zeroed out. And we gain a bunch more quadratic equations in terms of the matrix B. Hyttinen, Eberhardt and Hoyer showed in 2012 that if you perform enough such experiments, then you gain identifiability. How much is enough? The set of experiments needs to be a separating set, which means that for every pair of nodes I and j, there needs to be an experiment that separates them such that I is being intervened on and j is not. What are examples for such kind of experiments? One could have all but one experiments, single node experiments, or balance/binary experiments. This last example is being obtained by bisecting the set of random variables. And in particular, it shows that one can gain identifiability with the number of experiments that's logarithmic in P. What we do here is provide a finite sample analysis of estimating a sparse matrix B in the Forbinius norm. For this, we denote the sparsity in terms of the maximum row sparsity of B by D. We assume that E forms a separating system, hence yielding identifiability. And for technical reasons, that there's only a constant number of experiments that separate I and J for each pair I and J. Moreover, we assume that we have access to IID samples, ID observations from each experiment, and that the total sample size, n, is being split up equally among them, such that each experiment gets n divided by capital E observations. With this, we obtain the following lower bounds. You cannot do better in Forbinius norm than PD times E over n times a log factor. Here, the factor PD is common and is expected because it's the dimensionality of a d-sparse matrix B. On the other hand, it's quite surprising that the estimation rate does depend on the number of experiments you need to separate out all the possible matrices B, or all the nodes. In particular, it suggests that it is statistically desirable to have balanced experiments where you only need a logarithmic number of these experiments. So what can we say about upper bounds? In the same paper mentioned earlier, Hyttinen, Eberhardt and Hoyer came up with a moment estimator for B. One can see this by looking at all the quadratic equations we have in terms of B and observing that a bunch of those are just linear, only contain linear terms. Collecting them up, replacing some population quantities with empirical ones, and solving a lasso type estimator, or lasso type problem, yields their LLC estimator. For LLC, we can show upper bounds that are of order PD times E over n times log, which is great and looks like they actually match the lower bounds, but there's a catch, namely the constant C I wrote in the upper bounds here depends on some conditioning quantities of the linear systems we are solving, and is thus not independent or uniform over B, so those are not minimax rates. What can one do instead? we suggest using a maximum likelihood estimator, which we can obtain by writing down the maximum likelihood or the log likelihood for the system, and then adding an L1 penalty on top of this. An asymptotic analysis of this estimator is available in Alan Hauser's thesis. Here, we provide the finite sample analysis. It's a non-convex problem. We analyze it locally, and actually to make our proofs work, we also have to restrict the optimization problem to a small ball around a good initial estimate. If we do this, we are able to show rates of PD times E squared over N times a log factor. So in fact, those are minimax upper bounds now. They uniform over a class of matrices B. And if E is of logarithmic size, then they are near minimax optimal. They match the lower bounds up to log factors. What's not to like about this is that it does involve a non-convex optimization problem, and the number of observations needs to be quite large, much larger than the effective or the eventual rate suggests, which is probably an artifact of our proofs. Nonetheless, we can run some experiments on this by using continuous optimization techniques. We did this on synthetic graphs, where the graph is sampled as a random regular sparse graph with Gaussian weights. If we do this, there are no big surprises in the scaling in terms of P and D, but if we vary the number of experiments, we actually see that the maximum likelihood estimator does a good deal better than LSC here. More strikingly, we also ran some experiments where we are short a couple of interventions for separability and thus identifiability. Here, the maximum likelihood estimator seems to do a good deal better than LSC, which is somewhat to be expected because we know that in certain sparse average case models, actually identifiability can be obtained. Look, for example, in the paper by Abrahamson and Rigollet in 2018. To summarize, we provided minimax upper and lower bounds for estimating sparse cyclic linear structural equation models, and those match up to log factors in the case of a binary or balanced experiments. Open problems to solve from here is, can we close the gap of E between the upper and lower bounds? Is LLC provably suboptimal, or maybe not? And can one do a more fine-grained analysis of what happens, for example, with imbalanced numbers of observations between the experiments, or if some experiments are missing? And on top of this, can we understand the average case behavior for certain classes of matrices B? Thanks for listening.